And today I will talk about how to use Euler's formulas in particular. I'll recall what it is to write complex numbers in polar forms and to solve certain kinds of equations, which you'll see when I start doing it. So let's just start with recalling Euler's formula, because it's always good to remind yourself of what's going on after a weekend. It says that e to the I theta is equal to cosine theta plus I sine theta. Okay, and that is just a fact that I think you need to, put in your brain somewhere you won't lose. One way to remember it is to think geometrically, where here I'm using the letter theta on purpose. Okay, if you remember your trigonometry and you have an angle theta, you might remember that the Cartesian coordinates of this point are cosine theta, sine theta. So the x-coordinate is the cosine of the angle and the y-coordinate is the sine of the angle. And one way you can think of this formula is that telling you that the complex number e to the I theta, if you didn't know what it was, right? You're like, I know what e squared is, I know what e to the minus 10 is, but like what's e to a complex number? Well, you can think it's this guy, right? This number is the number e to the I theta. So if you go, right, from the x-axis, theta along the unit circle, that point is e to the I theta, and its coordinates are, the x-coordinate is cosine theta and the y-coordinate is sine theta. That's one way to think about it. Okay, so that's the formula. And how I'm going to use it for now is, well, first I'm going to talk about, hopefully this is recalling, right? So if I have z, a complex number, there's two ways I'm going to want to think about it. Two ways to write it. There's the, I want to say Cartesian way, but like with the Cartesian coordinates maybe, okay, which is what maybe you're most used to. You might write it as z is a plus I times b. A and b are going to be two real numbers. And in that case, we'll say that a is the real part of the number z, and b is the imaginary part of the number z. And if I were, I'll draw it over here. If I were to draw this number, right, this is a complex number, it's somewhere in the complex plane, then this distance is a, and this distance is b. So it's, I'm saying like Cartesian coordinates because it's like Cartesian coordinates, like x, y coordinates. And the x coordinate is the real part and the y coordinates is the imaginary part. Okay, so that's one way. And then if you're like thinking, Calc 3, 121, then there were also polar coordinates, right? Instead of describing this point as like some x, y, you could also describe as some r theta. And then you would do change of variables and some integrals would be easier, etc. Okay, well, it's the same for complex numbers. You can still write them in the polar coordinates. Okay, this same number z can be written as r e to the I theta. And here, right, e to the I theta is this e to the I theta. So, and r is how far it is from the, so r is how far from, 0 z is, right? So it's going to be, on my picture, it's going to be this distance r. So just like in Calc 3, that's what r was. And theta is this angle. Okay. Sometimes r is denoted the absolute value of z, like that. If you think in the real numbers, right? My number can be all the way here. Its absolute value will maybe be 10, or it can be down here. Its absolute value will be 2. That's how far you are from 0. So we use the same notation for complex numbers. How far you are from 0 is the absolute value. And to connect it to Cartesian coordinates, well, using Pythagoras, we know that this is a squared, the square root of a squared plus b squared, right? The positive square root of a squared plus b squared. If you have a number that has x and y coordinates a and b, then how far it is? It's the square root of a squared plus b squared. Okay, and theta is the angle that z makes with the positive x-axis. Or in this case, we'll sometimes call it the real axis because we're not really talking about x, y, we're talking about complex numbers. Okay, so it's that big angle. Theta, so R is called, so I said it, but I'll just write it down. The absolute value of z, and theta is called the argument of z. Okay, so argument. So just like A and B had names, the real and imaginary part, R and theta also have names. They're the argument and absolute value of the number. Okay, and if you remember how to convert from one to the other from Calc 3, it's the same formulas. And I'll say a little bit about that. It'll turn out that Euler's formula gives us a kind of easy way to go between them, and I'll do some examples. I want to make an important note, okay, that theta is not unique. Right, when I give a value to this angle, it's not a unique value, which you might remember from trigonometry, right? I could go around and not stop, right, and go all the way around and stop now, and that would give me the same number, right, because I stopped at the same point, but not the same argument, right? And that's like one thing that you'll have to deal with, but not today. But if theta is an argument of z, actually any theta prime, which is theta plus 2 pi n is an integer, n is an integer, is also an argument. Of little z, right? So 2 pi is going like a whole circle, so I can go a whole circle forward, 2 circles forward, 3, etc. circles forward, but I could also go backwards, right? So here I went like that way and I did an extra circle, so that would add 2 pi, but I could also have started here and gone backwards and gotten a negative argument, which would have been theta minus 2 pi if they would be related by that equation. Okay, and so most of the time, reasonable people assume either that theta is between 0 and 2 pi, right? So they start counting and they go like that. Or that theta is between minus pi and pi. So the angles down here, like they'll count negative. So they'll call this one like negative pi over 2. And the ones up here, they'll count them positive. So they'll kind of go like from here to there. Those are like the two most common things. But some people have reasons to do other stuff. And actually today we'll kind of play with this a little bit to get some answers. So, but most of the time we'll try to stay between those values so we get a unique argument and we don't like have to worry. Okay. So let's just do like a couple examples of converting between Cartesian examples. Converting between Cartesian and polar. Okay, so my first example is z is equal to I. Okay, so this is, if I were to write it in like a plus bi, right, that would be 0 plus I times 1, just to like be really explicit how this is Cartesian coordinates. The real part is 0 and the imaginary part is 1. And so if I want to write it as r e to the I theta now, well, I need to figure out what r is and what theta is. And to me, especially for a simple number like this, the best way is to draw it. Right? So I is here, right? It's like 0 in the x direction, 1 in the y direction. Okay, so this has length 1. So r is equal to 1. Right? It's a distance of 1 from 0, which I could get from doing the square root of a squared plus b squared if I felt very unsure of myself, you know, and wanted to like work it out with the formula. The square root of 0 squared plus 1 squared is 1. Okay, so I found r. And then to find the theta, I'm just going to read the angle off because this is an easy angle, right? So from the x-axis to I, this is the angle pi over 2. Okay, sorry. The notes say pi over 4, but that's a typo. And so for a minute, I was like, which one is it, you guys? But I'm like 90% sure it's pi over 2. The class agrees. We're going with pi over 2. I believe that these notes were written like this morning in a haze of cough syrup. So I'm not going to take everything here as gospel. Okay? So I would write I is equal to e to the I pi over 2. Ta-da, we did it. Okay, let's do another harder example. Z is minus I minus 1. Okay, so again, just to be very explicit, this would, you know, if I wanted, this would be like minus 1 plus I times minus 1. So this is a number with real part minus 1 and imaginary part minus 1. If I draw it in the plane, it's here, like at minus 1, minus 1. Okay, so again, I need to figure out what r is, what this distance is between my point and 0, 0, and what this angle is between the positive x-axis and my line that I just drew. Okay, well, r, right, is going to be the distance between my point and 0, 0. So now I'm going to go with the formula because I don't know. I don't see it right. I mean, like, it's not a very complicated number, but so it's going to be the square root of minus 1 squared plus minus 1 squared. So it's the square root of 1 plus 1. This is the square root of 2. Right? So this is a distance square root of 2 away from 0, 0. Sorry, just 0. And theta is this angle. And there's many ways you can think about it. But what I like to think, right, is like this is like halfway, right, between like this and that. So if I go this much, that's pi. And then like halfway between pi and 3 pi over 2 is like another pi over 4, right? So just this little bit is a halfway is a pi over 4, so this is going to be pi plus pi over 4. So that's 5 pi over 4 is the angle. The other way that you could compute this is like pull out your calculator and do some kind of like arc cosine or arc sine from knowing the sine and the cosine, which like, except if your calculator is smart enough to give you like some kind of pi thing, I think it's easier to just remember your basic angles. And I mean, you know, the point is not to get much more complicated than something like this off the top of your head. Okay, so this one, I would say that minus I minus 1 is equal to square root of 2 e to the I. I mean, you could put the I with the 5 pi over 4, right? The exponent, like the numerator is I 5 pi or 5I pi, whatever order, multiplication is commutative, divided by 4. Okay, so that's in polar coordinates. What can I do with this? Well, I'm going to use this to solve certain kinds of simple equations. So I'm going to talk about first what we call in the biz roots of unity. Okay, so any z, a complex number, such that there is an integer, and a positive integer even, with z to the n is equal to 1 is called an nth root of unity. Okay, so this is not meant to be very scary, right? So the idea is like the square root of 2, right? Like square root of 2. That's some number z such that when I do z squared is 2, right? So like you know, a second root of 2 is a number that when I square it, I get 2. So the only kind of like fancy thing is that instead of saying like a square root of 1, we say square root of unity, right? So unity is like fancy way to say 1, right? And if you know, think from calculus or wherever you last saw this, there's 2 square roots of 2, right? Like square root of 2 is not the only number that when I square it, I get 2. There's 2 of them. Minus square root of 2 is another square root of 2. Okay, so there are 2 square roots of 2. Square root of 2 and minus square root of 2. So here, when I'm talking about a root of something, I'm always going to mean all of the roots of them, right? Like in calculus, you kind of get used to thinking of this as like the square root of 2, and this one is like some other thing that we don't like as much. But in this class, you'll want to think of both these things as this, like a square root of 2. This one and that one, the other square root of 2. Because in the complex numbers, right, there's not like one that's positive and one that's negative. There's, you know, stuff on top, on the bottom, on the left, on the right. So we'll just like think of all of them. You'll see when we do kind of bigger numbers. Okay, but let's start with roots of 1. Yeah? Z is the nth root, is the root of unity. Nth is like the how manyth root of unity, right? So just to like a solution to z cubed is 1 is a third root of unity. right? So it's like the n here is like what equation you were solving, and the root of unity is the solution. Is the solution to the equation. Okay, so like, yeah, sorry. This is not like third over n. This is like third is 3 is n in this example. But that's a good question. Okay, so yeah, let's do this, right? Let's look at z cubed is equal to 1, right? Let's do the third roots of unity. So you know the second roots of unity is 1 and minus 1, right? Those are the two things that when you square them, you get 1. So let's like move up to 3. So there's an easy one, which hopefully you know from like your whole life, right? 1. If I cube 1, I get 1. And if you've only ever done like real calculus, like the thing we call calculus, you're like, that's the only one, right? That's the only thing that when I cube it, I get 1. But not in the complex numbers. In the complex numbers, I'm going to have 3 total third roots of unity. So I need to find 2 more. So how I'm going to do this is I'm going to use Euler's formula plus a trick. I mean, it's not really a trick, like plus an idea, right? Is if I do, right, so my goal is to get the number 1, which I can think of as the number with the angle 0, right? I can think of the argument as 0, like I didn't move. But what my trick is going to be, this is also the number with angle 2 pi. And this is also the number with angle 4 pi and 6 pi and so on, right? So that's my trick. My trick is I'm going to think of 1 in many different ways. All these ways, infinitely many ways. It's still going to give me only 3 answers. Okay, and the negatives in there too. So if I do kind of 1 is equal to the e to the I times 0, right? And then I want to solve like z cubed is equal to 1 is equal to the e to the I times 0, then one way that I can do this is kind of raise both sides to the 1/3. And here I just like do exponent laws, and I multiply my exponents, and that's e to the I times 0 divided by 3, which is just like e to the I times 0, which is 1, right? So that's the first one that I got, is thinking of 1 as having argument 0 and dividing that argument by 3 using exponent laws, right? Like, if I have z cubed is 1, the naive way to solve it is I'm going to raise both sides to the 1/3. And then when I write 1 like this, it's easy to raise this to the 1/3, right? Exponent is multiplying exponents. And that gives me 1 answer. But that's not the only way to write 1, right? So I can do also z, okay, z cubed to the 1/3. I keep writing 2. Okay, is 1 to the 1/3, okay, duh. But the way I think of 1 now is I'm going to write e to the 2 pi I. That's still 1 to the 1/3, right? Like, I have many ways to write 1. And so that's going to give me e to the 2 pi I over 3. And that's a different number, right? Like e to the 2 pi I over 3, if I think back to my Euler's formula, is the number that's at 2 pi over 3, so it's like somewhere here. right? It's not 1. It's some other number. It's a new number. And when I cube it, I still get 1. And then, well, I continue on my merry way, right? Z could be like z cubed to the 1/3, which would be 1 to the 1/3. But this time, I choose to think of 1 as being e to the 4 pi I over 3. 4 pi I, sorry, that's my 1. And then the 1/3 on the outside, right? So now I think of 1 as being 4 pi I. And that will give me e to the 4 pi I over 3, which is the number with argument. Okay, my drawing is not the best. Let me draw this a little bit better. So 2 pi over 3 is a little bit higher up. And 4 pi over 3 is actually here, down there. And if you, think of this geometrically, actually, these 3 numbers are each 1/3 of the way around the circle. Like this is 120 degrees. This is 120 degrees. And this is 120 degrees. So there are 3 roots of unity. They're all on the unit circle, and they're like 120 degrees apart. And that will be true for every root of unity. And if I keep going, okay, I'm only going to do like one more. Right? If I'm like, okay, well, 1 is also e to the 6 pi I. Okay, and I do to the 1/3. Well, now I'll get e to the 2 pi I. But e to the 2 pi I is not new. That's the same as e to the 0 I, right? So I've come back. And if I kept going, then I would get that one again, and then I would get that one again, and if I would get that one again, and so on. And if I had gone with negative numbers, right, if I had done like z is z cubed to the 1/3 is 1 to the 1/3, and this time, I go wild. I'm just like, this is e to the minus 2 pi I, right, to the 1/3. This is still 1. These are all 1, right? Well, this would give me e to the minus 2 pi I over 3, but minus 2 pi I over 3 is the same as 4 pi I over 3, right? Is this like minus 2 pi over 3 is the same as 4 pi over 3, so I would get that one. So you always end up with those same 3 no matter which version of 1 you take the root of. And that's how you get more roots of 1, is by like starting with different ways to think of the number 1, different arguments for the number 1. Super cool. I'll do like really quickly one more example. The idea with this, right, is that you would never work these out. Like once you see the pattern, like you can't unsee it, and you just know the roots of unity, right? So you're not expected to work this out every time. So I'll just like really quickly do a couple more, so so that was 3, right? Let's look at the 4th roots of unity. These are the solutions to z to the 4 is 1. So this is going to be my unit circle. And the 4 roots are going to be on the unit circle. Now they're going to be 90 degrees apart. So 1 is definitely a 4. 1 is an everything root of unity, right? You raise it to any power, it's still 1. This is a 4th root of unity. So this number I, which we can write as e to the I pi over 2, is a number that when I raise it to the 4th, I'll get 1. Minus 1, which is e to the I pi. Right, so the argument of this number, that's the angle pi. I'm using 0 to 2 pi. I guess like I'm a big fan of 0 to 2 pi. I only told you about minus pi to pi, like in case. Okay, and the number down here, minus I, is e to the 3 I pi over 2, right? So this is the number that would have angle 3 pi over 2, so this is e to the 3 3i pi over 2. And that gives you 4 fourth roots of unity. And this kind of tells you like something about complex numbers. In complex numbers, raising something to a power is kind of like rotating it 4 times, right? So this number, I mean, if you rotate it, it just stays there. But like if you think of this number, if you kind of like if you multiply like I squared, you'll get here, right? So it'll be like, if you think of I as like this rotation, then like I squared will be like that rotation, right? And I squared is -1. And if you do I cubed, it'll be like 1 rotation, 2 rotations, 3 rotations, and you'll get to -I. And then 4 rotations, you'll get back to 1. So these are all the numbers that like if you do like a rotation of this many angle, you'll get back to 1. So like this, right, if you do it twice, you get back to 1, but if you do it 4 times, you get back to 1, like again. Okay, and then let's just do like the 5th roots of unity. Odd. Okay, so these will be numbers we know less well. But that's okay. They're there, right? There's 5 of them. There's always 1. And then there's 4 more, like, spread out evenly. So, like, I don't know, maybe like, I didn't look them up beforehand, but it's like something like this. You know, like you draw like 4 points, like 5 points equally apart on the circle. And this one is e to the I pi over 5. And this is e to the 2i pi over 5. And this is e to the 3i pi over 5. And this is e to the 4i pi over 5. And this one is e to the, no, I messed them up, right? Because I need to get to 2. So this one will be 4. And this one will be 6. And this one will be 8. And that one will be e to the 10i pi over 5, which is e to the 2i pi, which is 1. Okay, so in general, the nth roots of unity are e to the k times 2 pi I over n. And k is 0, 1, 2, all the way to n minus 1. Right, so, sorry, this one should have been still 2. So this is 2i pi over 5, 4i pi over 5, 6i pi over 5, 8i pi over 5. So this is the formula with k is 1, 2, 3, and 4. And if you look back, this is 2i pi over 4. So the 2 and the 4 canceled to give me this. This was this ended up being 4i pi over 4. So the 4 and the 4 canceled to give me I pi. And this is 6i pi over 4, which ended up being 3i pi over 2. I reduced the fractions in my head. And if you look back to the 3's, the same thing happened. It was like 2i pi over 3 and 4i pi over 3. We're good. So I'm going to ramp it up now. Okay. So the next thing that we're going to do is use this to solve a slightly harder equation. Okay, so say I want to solve solving more complicated roots. Right? So say I want to solve, so example, say I want to solve z to the n is not 1, well, okay, maybe z cubed is 2 instead of 1. Okay. Well, one way that I can think about this is that I know one number that when I cube it, I get 2, right? One solution is z is the real cube root of 2, like the one you know and love from your calculator when you push the button, right? That's like, this used to be a solution, this is still a solution. We're not losing solutions, we're going to gain solutions, right? So now, right, if I'm clever, another solution is z is equal to e to the 2 pi I over 3 times the cube root of 2. So this is a number I just found. When I'm going to cube it, I'm going to get 1. So if I cube this times this, I'm going to get 1 times 2, which is 2. So that's another solution, right? So because I have until 40. Okay. It's like so hard because my class goes until 40 to half. So I'm like, at 6 I stop, but not here. Here I stop at 8. Okay, because z cubed, right, that would be e to the 2 pi I over 3 cube root of 2 cubed. And then z cubed is e to the 2 pi I over 3 cubed times cube root of 2q, right? When I cube a product, I can cube each term separately. And this one is 1, and that one is 2, so I get 2. Okay? So now maybe you know how to find a third solution, which is by using my other third root of unity. Okay, so the last solution is z is e to the 4 pi I over 3 times the cube root of 2. Because this, when I cube it, I get 1. And this, when I cube it, I get 2. And so when I cube the product, I get 2. And that's it. And the reason that's it is that there's no other way for me to cube and get 1, right? So there's a connection between how many ways I can cube and get 1 and how many ways I can cube something and get 2. They all differ by like something that when I cube it, I'll get 1, because then it doesn't make a difference. Okay, so to state this theorem, right? So I was able to write down like the nth roots of unity like pretty cleanly to talk about like all the roots of some other number. Well, I mean, there's an easy way and there's a like more advanced way. So maybe I'll do the easy way right away and then start talking about the hard way. But I could just the nth roots of some number r, right? So if I'm not doing 1, I can do a number r. R is not a great choice because R. Anyway, pirate day. Okay, are all of these roots of unity time the nth root of r, where the nth root of r is any one nth root of r. Right, so usually we know one. I'll just finish my sentence. Usually we know one nth root of r from calculus, like from there's a button on your calculator that gives you an nth root. And then like the other ones will be just like multiplication by roots of unity. Yes?
Geometrically, or you just kind of jump into a bigger circle?
Yeah, and that's exactly. Thank you for segueing into my next point. Right, so if we think back to like the polar and Cartesian coordinates, right? That's all I'm doing. I'm just using the polar coordinates, right? So this number, this is the r of that number. Okay, not same r. I should not have used r. I take it back, right? And this is e to the I theta for this theta, right? So as much as you might have hated polar coordinates when the class started, when you take roots, polar coordinates are awesome, right? Because if I have, yeah, okay, here's the like easiest way, right? If I have like if I'm solving z to the n is some number s, right, like 2, and I write this s as r e to the I theta, then kind of like what I'm doing is I'm just going to do z is r to the 1 over n, which is like this part here, right, like one like real root of this number. And then I'm going to put in parentheses e to the I theta over n. But here I'm going to be careful to like write this in all the different ways, right? Like all the different like roots of 1 that I could get. So like the this, you can just rewrite it like by adding, you know, circles around and then dividing by n. So it's because like taking roots works so well with multiplication that like taking roots works so well with polar coordinates. Like I'm just kind of dividing on both sides with being careful to like think of this as like not one answer, right? But like many answers depending like when theta changes, right? So remembering that theta is not unique. So like here, theta will keep changing, and it'll keep changing like according to this formula that I wrote down here. And so yes, right, this is still the same thing, except I'm changing how far it is. So if I draw, I'm going to do cube roots because that's the one like I'm best at, right? The cube roots of 1 are here, and then the cube roots of 2 are just like a little bit further away. They're, you know, cube root of 2 times 1, so like maybe cube root of 2 times 1 is here, and then cube root of 2 times this number is there, and cube root of 2 times that number is out here, but they're still like spread out evenly around now a circle of radius cube root of 2. And if I wanted the cube roots of 50, right, I would start with like a cube root of 50, okay, not to scale, right, but a cube root of 50 here, and then there would be like another cube root of 50 here and another cube root of 50 here, right? They would always be organized because the only thing that's really changing is like my root of 1. So yeah, it's just like how far they are. And so I was saying, right, multiplication here is like just kind of adding up the rotations. If you're not on the unit circle, multiplication is adding up the rotations and the arguments. So if you take like this number and you square it, you're not going to end up here. You're going to end up like a little bit further. And then when you like multiply it again, you're going to end up like on the number 2, right? So every time like that you multiply, it'll get a little bigger. I mean, that's the kind of thing like you don't really get tested on, but you just like work with it and then you like notice this kind of stuff happens. So I'm just like telling you so you start noticing. Let me see what else I had to tell you. Okay, this is going pretty well. So one idea that Taylor, I will tell him to introduce next time is the idea of a primitive, but I'm just going to use my 2 minutes to start pre-introduce primitive nth roots of unity. Right, so I just talked about nth roots of unity. But now I want them to be a little more, right? I want them to be primitive. So z is a primitive nth root of unity if z to the n is equal to 1, right? So I want it to be a primitive nth root of unity. Like to be a fancy nth root of unity, you got to be an nth root of unity first. But z to the m is not equal to 1 for any m smaller than n, right? But it's not a root of unity before that. So I'll just like give like 1 or 2 examples. Okay, so the fourth roots of unity are, we wrote them down, right? 1, I minus 1 minus I. Okay, but 1 to the 1 is equal to 1, so it's not primitive. And minus 1 squared is equal to 1, right? So it's like you get to 1 earlier, so it's not primitive. Right, so you see, like, sometimes, you know, you're like, yeah, if you keep raising, it'll still be 1, right? But, like, it was 1 before, so it's kind of not new, right? But if I look at I, okay, well, I to the 1, that's not 1, right? That's not, I is not 1. I squared is minus 1, which is not 1. And I cubed is minus I, which is not 1. So I to the 4th is like the first time, right, that I get 1. So it is primitive. Okay, and same for minus I. If you work it out for minus I, okay, minus I is not 1. Minus I squared is not 1. Minus I cubed is not 1. And minus I to the 4th is 1. That's the first time. So those are primitive. Okay, so I'll let you go because I think I've already gone over by a minute, so I won't keep going. But I'll just have Taylor kind of like start over with this next time. And that'll give us a different way to state all the roots that I told you. That's like a little bit cleaner.